Hello everyone. In the last video, we had started the conversation for the latency and the power, and also we came up with an equation for the latency, where we said the latency was 9 buffer delays plus 10 wire delays, and the total power was a total power that was consumed by this particular chip or by this particular circuit, assuming that our chip will be consisting of 16 flops and this many amount of clock buffers. So the total power that we computed was 39. Why 39? Because the number of clock buffers which is present over here was 39, and also we are looking into the clock path for now, where we are looking into the power for the clock path. So the clock tree power was and also we know that the 75% or 70 to 75% of the complete chip power is been consumed by the clock path itself. So let's so that's why we are looking into the power number, specifically the power number for the clock. So we had this equation which said the total power was 39 multiplied by the switching power plus the short circuit power plus the leakage power. So in this video, let us try to look into the definitions of the switching power, short circuit power and leakage power. We have already seen this before in the initial videos where we were discussing about the quality check parameters, and when we were defining each and every quality check parameter. So let us try to revise it again in a very brief manner. Let us try to do that now. So switching power is also called as a dynamic power. So what happens when you move from logic 1 to logic 0? So when we say that logic 1 to logic 0, basically essentially we are saying that the input is at logic 0. So whenever your input it is logic 0, your PMOS is turned on. That's the basic function of PMOS. So PMOS turns on, and before, when the input was at logic 1, your NMOS turns on. So when in this case, whenever your input was at 0 voltage or at 0 potential, this capacitor had got drained out or had got discharged through this NMOS, because your NMOS was on. But now in this case, when it switches from logic 1 to logic 0, assuming now we are considering assuming the situation is that we are seeing only in this area where it is at logic 0. So at this particular point of time, your PMOS turns on, and it gets a short circuit path, or it gets a path for this capacitor to charge. So this particular capacitor or this particular load capacitor is nothing but a combination of wire loads and the successors of this particular circuit. So this particular load capacitor gets charged from VDD through this path, through the PMOS path, and so I've drawn the arrow over here. This is the charging path over here. So when this capacitor gets fully charged, what do we mean by that? It means that it has drawn some finite amount of supply, finite amount of power from the supply. So this is what it actually means. So there is some amount of power that gets dissipated or that gets drained out from the supply. So this supply is nothing but a huge tank of water. It has got hundreds and thousands of liters of water, out of which this is let's say a smaller tank which consumes around let's say half. It might be like some milliliters of, let's say 10 milliliters or 20 milliliters of bucket. So whenever you have a path from the water tank to this small tank, a 20 or 30 milliliters of water is being consumed by this particular capacitor or this particular bucket to fill it up. So this happens whenever there is a switching, or whenever there is a switching from logic 1 to logic 0. This thing happens. This thing will be consuming amount of water, 20-30 milliliters of water. But and why it happens at every switching? Because whenever there is a next switch, that whenever it happens from logic 0 to logic 1, at logic 1, this particular tap gets open. So all the water from this particular bucket, whatever minimum water we had in this bucket, that gets drained out through this NMOS. Hence, at every switch, after every switching, there we need some small amount of water which has to be present in this particular bucket. So that is the basic phenomena of switching power. That's why at every switch you consume an amount of power, and this is, we spoke about only single buffer, basically an inverter inside a single buffer. Similarly, we have like 39 buffers over here. So every and whenever this switches, this switch is propagating through all the 39 buffers because it's a single path. Okay, so at a certain point of time, all the 39 buffers are at the same time consuming a finite amount of water. It's let's say 30 in this case, let's say if you are consuming 20 milliliters of water or 20 units of water. So imagine 39 buffers would be consuming around 39 into 20 units of water. Imagine if there would have been millions of lobs, there would have been some billions of buffers that is present over here, and each buffer would have consumed a finite amount of water, a finite amount of charge in their buckets. So this is how this dynamic power or switching power is impacting the complete power dissipation from the entire circuit. So this is a very big number over here. When you multiply it by a quantity, it becomes a really very big number. That's why this is a one more point of checklist, and one more point of consideration which can affect the power, which can affect the performance. So there are ways to control this. We have got clock gating techniques and so on, which we'll be talking more about in the further slides, but not in further slides in this lecture itself. But right now we are focusing on the checklist first. So yeah, there are ways, but we have to quantify something. We have to quantify the value of power over here. So this is the switching power that we have. So switching power is like the total switching power that is consumed by this circuit is 39 into PSW, which is some quantity. I will also bring up what this quantity is. Let us try to look into in some time from now. Let us first finish off the definitions first. So next we have the short circuit power. So now whenever your input switches from logic 1 to logic 0, or in other case logic 0 to logic 1, in either case you have, okay, at this particular input, whenever your input is at logic 0, your PMOS is on, your NMOS is off, and the voltage that is required at this gate to source voltage to turn on this NMOS is threshold voltage. So whenever your gate to source voltage exceeds the threshold voltage of this particular NMOS, your NMOS turns on. That we know that theoretically. So now what happens is, whenever your input is switching from 0 to 1, the voltage across gate to source is crossing the threshold voltage. So whenever let's say at this point of time it crosses the threshold voltage, your NMOS starts to turn on. Okay, that's the first point. Second point, when your PMOS will turn off, it will turn off only when your VGS, your gate to source voltage, goes less than threshold voltage of the PMOS. So in this area, your gate to source voltage is not yet going less than the threshold voltage of the PMOS, but it is tending to go below threshold voltage of the PMOS. At this point of time, at the voltage which is but just slightly below than VDD, your gate to source voltage goes completely below threshold voltage, and your PMOS completely turn off. But if you see, during this transition period, you have both your NMOS and PMOS turned on, because at this particular threshold, at this particular voltage, your NMOS tends to turn on. Above this particular voltage, your PMOS shuts off completely. But during this period, your PMOS is trying to turn off in this area, but it's not completely off. So that's the reason you see a short circuit path. That's the reason, first of all, you see a PMOS and NMOS both turning on during this transition period. That is first thing. Second thing, you see a short circuit path from VDD to ground. So there is a supply, there is a voltage, or there is a flow of current that happens. Basically some charges flows from this huge tank of water onto the ground directly, basically, and the flow of charge is nothing but current. So there is a short circuit current that flows from the VDD to ground, and that impacts, this is again a huge, this is not the huge number, but when you multiply that short circuit current, and when you see the impact of short circuit current for every buffer that is switching during this period, that number is very huge. So this power, we call it as short circuit power, because this is we talked only about one piece of inverter, one piece of buffer, let's say. But for example, if you have all these clock buffers switching at the same time, it will be switching at the same time. So at that particular amount of time, you see lot of current flowing from VDD to ground during this transition period. So again, this happens only whenever there is a transition from 0 to 1, and this is again a potential number that we have over here, and that has to be considered. So again, we have a short circuit. So this particular phenomena is referred to as short circuit power, and this is a power that we need to quantify, because as you see over here, it's again a number which gets increased when you multiply it by the number of buffers. So in the next, since I'm running out of time, what we'll do, we'll look into the leakage power thing in the next video, and also we'll look into how can we reduce this, how can we reduce the latency, or how can we reduce the power, or is this the best that we can achieve, or can something be done about it. So let's try to look into all this in the next video. Thank you.